In this video, we're going to talk about statistical inference in regression analysis, and we're going to use data file Butler with deliveries. So at the end of the day, when it comes to regression analysis, we want to be able to comment on the significance of the relationship between independent variables and the dependent variable. So we want to see if they're statistically speaking related to each other, significantly related to each other, right? So we can have three types of results when it comes to statistical inference in regression. So the first thing is hypothesis testing with respect to each individual regression parameters, each individual coefficient. So we have, again, similar to the any hypothesis testing, we have a null and alternative hypothesis. The null is that if the population parameter, the coefficient is 0, the alternative would be if it's not equal to 0, if it's different from 0. And when we reject the null hypothesis and take the alternative, that means that we have enough evidence to say that there is a significant linear relationship between y and xi, right? Between the dependent variable and the corresponding independent variable. So our objective would be to find, hopefully to find enough evidence to go ahead and say that x and y have a significant relationship. So when it comes to Excel provides us with the test statistic. So this will require a t-test, which has a test statistic equal to the point estimate of the coefficient divided by standard deviation of the point estimate. Estimated standard deviation of coefficient, estimated coefficient coming from our sample, right? So Excel provides us with the value of test statistic, but at the end of the day, what matters when we wanted to perform hypothesis testing, the last step was to find the p-value and then make the conclusion based on the comparison of p-value and alpha. If p-value is less than alpha, we can go ahead and say that we can go ahead and reject the null hypothesis, which is equivalent to saying that there is a significant relationship. So basically, Excel, on top of the test statistic, also provides us with the p-value. So we just need to look at the p-value and check to see if p-value is less than alpha. And if yes, that means there is a significant relationship. Xi is a significant factor. That's it. The second result that we can get from a statistical inference in regression analysis would be a confidence interval for each one of these regression parameters, each one of these beta i's. So not only checking to see if they're significantly different from 0, that's great, that's the first step, but also having a confidence interval, like knowing that with 95% confidence, what would be the range, what would be the interval that they're going to belong to. And it's by default, Excel provides us with 95% confidence interval, but we can change it to 98, 99, whatever level of confidence that we are looking for. All right. So that's the second output. That's the second result that we can get from this statistical inference in regression. Before talking about the third one, let's talk about other issues, other important issues. For example, What do we do if we have a non-significant independent variable? So what happens if we, at the first step, when we check the p-values, if the p-value is greater than alpha, so what do we do? If, I mean, a lot of the times, if you are, if you have no theoretical reason as to, or practical reason as to why we should include the non-significant factor into the regression, we should remove the factor. If there's no theoretical reason, if there's no practical reason, and it's not significant, I mean, the sample does not show a significant relationship, so we should remove that factor and run another model with other factors that are significant. If we have a reason as why this factor should be included in the model, we should keep it. For beta 0 and for y-intercept, that's the only exception. In business examples, we have no practical or theoretical reason in most cases as to why this should be removed. So in a lot of cases, in almost all cases that we are dealing in business applications, even if it's not significant, even if you get a p-value greater than alpha, greater than 5%, you still keep the y-intercept in the model. So that's a special considering, that's a special case here. For y-intercept, we keep it regardless of the p-value. All right, so that's one thing. Multicollinearity happens, that can affect the p-values, that can affect our hypothesis testing with respect to individual parameters. This happens when we have high correlations between independent factors. So that's a not necessarily a bad thing, but we don't want this. We don't want multicollinearity. It may affect the p-values. It may make p-values larger than they should be. I'll make another video for multicollinearity and we'll see an example of how this may affect the p-values. But generally speaking, we need to check the correlations. If correlations are above 0.7, that would be a case of multicollinearity. Multicollinearity exists if correlation between any two of the independent variable is above 0.7. I mean, I'm talking about the absolute value of correlation. If that is the case, and if the p-values of one or both of those factors are greater than alpha, we need to go back and take another look at multicollinearity may have affected the p-values. If p-values are less than alpha, that's fine. Even though multicollinearity exists, we don't really worry about it because it's not affecting the p-values. But sometimes it affects. If that affects, you need to, multicollinearity affects the p-value, you need to remove one of them or just integrate or just add or multiply and come up with just one variable rather than two highly correlated, all right? In the example that we're going to do, I'll show you how to check it, how to check multicollinearity. The next issue is the issue of very large samples. So when we are dealing with extremely large samples, like 1 million observations in a sample, it's really hard to get a result that is not significant. So it's hard to really discriminate between meaningful and non-meaningful relationship. Most relationship come out significant, statistically significant when the sample size is large. And it has to do with the way the test statistic is calculated. If the sample size is large, p-value tends to get smaller and smaller. So that is why when we have big data, when we're dealing with very large samples, the classic methods that we are using may not be 100% accurate. I mean, so you may conclude that it's significant, you have p-value less than alpha, but in reality, it may not be the case. That's why in a lot of cases, when we are dealing with predictive analytics in big data, we need to have a training set, a validation set, and a test set. So that way you can, once you train a model, once you feed a model, you can check the robustness of the results. You can check the significance of the relationship on a completely independent, on a completely different set of observation, right? Which is, again, it's not in the scope of this chapter. It's not in the scope of our course right now. Moving on, the last, I said there are 3 results that we get from a statistical inference of regression. The last one, the first one was the hypothesis testing of individual parameters. The second one was the confidence interval for each individual parameter. And then the third one is testing for the overall regression relationship. We basically here, we want to see if Y is explained by the regression model, by the overall regression model. Or in other words, we want to see if R squared is now significant. We want to see if the factor, if the dependent variable is explained using our regression model, right? And then this requires an F test using F probability distribution. And when it comes to Excel, Excel provides us with the F statistic and also with the p-value, which is called significance F in Excel. So we just look at the significance F. If it's less than alpha, we go ahead and conclude that the overall regression is significant. All right, so now I'm going to go ahead and open the data file, Butler with deliveries, and we're going to perform regression analysis, and we're going to basically complete the statistical inference here. All right, so we're going to check the necessary conditions. Before you can perform statistical inference, you need to check the necessary conditions for residual. And it's always good if you're dealing with multiple regression, which is the case here. It's always good if you can also check for multicollinearity. All right, so I'm gonna run the regression here. This is Butler with deliveries data file. We want to predict the travel time based on the distance, the length of travel, and based on the number of deliveries that should happen during each assignment. So I'm going to go ahead and call data analysis tool pack, regression tool. So Y range would be the time, D1 to D301, and X range will be B1 to C301, miles and deliveries. I have labels. I'm going to put it somewhere in the same sheet. Now, for checking the residuals, for checking the necessary conditions for statistical inference, I'm going to check residual plots. And I'm not, again, worried about the other ones for now. This is the only thing that we check in this chapter. regression analysis context. All right. So okay. So I have the residual plots. The first step always would be to get the actual equation, the equation of the line. So we have time, travel time is equal to intercept. So that's the estimated line plus 0.067 hours times miles plus 0.69 deliveries. All right, so that's the equation. And now we want to check, now we want to perform a statistical inference, all right? We have the necessary conditions. I mean, if we want to check the residuals here, these are the residual plots. Residual plots, we know by definition that residuals should be normally distributed. Residuals should be normally distributed with a mean of 0 and a constant variance throughout the range of X. And since we are dealing with two independent variables, we have two residual plots, one for miles, one for deliveries, right? So now, I mean, here you see X, X1, X2, a constant variance throughout the range of each X, each independent variable. All right. So now we see that almost always almost always residuals are following the rule, following the necessary conditions. At each neighborhood, it's symmetrical because we have approximately equal number of points below and above the center. Center is 0 always, approximately equal points below, above, so symmetrical, center 0, and then the range as you go from left to right is constant. You don't see increase in variation, you don't see a decrease in variation significantly. So that's perfect. This one also is good. So no, I can say no strong violation of necessary conditions observed. So that checks off the conditions that we have for residual. So that's perfect, necessary conditions for residual. So that's one thing. Now I can go ahead and perform statistical inference for individual parameters. For that, I have the test stat, T stat, and I have the p-value. What matters at the end would be the p-values. I need to just look at the p-values for miles and deliveries. And if they are less than alpha, I can go ahead and conclude that they're significant. So I should be looking for numbers below 5%. Alpha 5% is our default value, all right? So both of these p-values are less than 5%. This is less, this is 0, right? So when you see E minus 83, it means that there are like 82 zeros before 3. So it's a very, very small number. And same thing here, E minus 69, it's equal to 10 to the power of minus 69, or 2.8 divided by 10 to the power of 69. So that's another way to show it. So these are two small numbers. So both miles and deliveries have a significant relationship, significant relationships with travel time. They both are significant, so they both have significant relationship. We don't care about the intercept. Even if the p-value is greater than 5%, we can just leave it as is. All right, so these two factors are significant. And then if you are looking for a confidence interval for the actual coefficient, so what we get here for the coefficient, these are sample statistics. These are the estimated coefficient coming from this sample. But in reality, the true relationship, the true coefficient should be with 95% chance between these two values for miles and between these two values for deliveries. All right. So this is another factor that is important. We now have the 95%. If you were looking, by default, Excel provides you with 95%. If you are looking for a different confidence level, when you are in regression tab, when you're in the regression tool, here you can check the confidence level and change it to whatever value that you want, like 99%, and then you will have 95%, lower and upper, and lower and upper for 99, for example. I'm not going to do it because it's going to change it, but this is how you can change the confidence level and get the lower and upper limit for the coefficients. All right. So you can say the coefficient, the population coefficient for deliveries with 95% confidence would be between 0.63 and 0.75 almost. All right. So this is how we make the conclusion here. So this was the first statistical inference. This is now the second part of our statistical inference, the confidence interval. I'm not going to write it down. It's obvious to me. The third part would be the overall regression analysis, and that would be through significance F. So since significance F is the p-value for the F test, below 5% or alpha 5%, the overall regression is significant. All right, so the overall regression is significant because significance F is 0, is below 5%. So let me just highlight these two columns as well. So we have the 95% confidence interval for the coefficient. We know whether they're significant or not. We know if the overall model is significant or not, the overall model. And we also have the R squared. So here you have the R squared. Here you have the adjusted R squared. So adjusted R squared is also very important, usually even more commonly used than the R squared. And it just, this is now very close because the sample size is pretty large and it's not really affecting the R squared. But anyhow, the R, so we have the R squared. That is how we can basically control or check the goodness of the fit. And R squared, if you remember, R squared I said is SSR divided by SST And that would be basically the percentage of total variation in Y. Y here would be time. SST, total variation in Y, that is explained by the regression model. SSR, so this is basically SSR divided by SST. And here you have SSR and SST. So this is SST, this is SSR, and this is SS, sum of squares due to error, or residuals is the other term for error basically. So SSR divided by SST will be R squared. So percentage of total variation in times, that is explained by the regression model. That is because of the regression, right? So this model is explaining almost 82% of the variation in time, which is great. Usually above 50% is considered strong fit. Above like 70% is very strong. All right. So so we just check the necessary conditions. We check the individual, the significance of individual factors by looking at the p-value. We just got the, if needed, we have the 95% confidence interval for each one of these coefficients. And we also check the significance of the overall model by checking the significance F. And we also can find the R squared, and we can interpret R squared, the percentage of total variation in the dependent variable that is explained by the regression model. That's the interpretation of the R squared. One last thing before we close this file, one last thing would be multicollinearity. That's another factor that we may need to check. It's okay here, since the p-values are less than 5%. Even if it exists, it's not a concern for us, because p-values are already less than 5%. So even if it exists, it's not going to be a problem. But I'm just going to show you how to check it. So if you have only two factors, only two independent factors, miles and deliveries, it's easy. You just find the correlation between these two. Multicollinearity check. Correlation between miles and deliveries. If you want to go ahead and select the whole column, you need to make sure that there is nothing at the end of these columns. All right. So, and that way it's gonna, ignore the rest of the column. If you have numbers at the end, you should make sure to select only the numerical value. All right. So correlation between the only independent variables. We love to have large correlations between independent variables and time here. That's not a concern, right? So the concern would be the correlation between independent variables. So that is less than 0.7. So we use the same. So we use 0.7 here as well. So for multicollinearity, if it's below 0.7, that would be a red flag. You just need to check the p-values. If p-values are less than 5%, you don't need to worry about it. So it's multicollinearity check. It does not exist, because the correlation between independent variables is less than 0.7. So it does not exist because it's less than 0.7.